Yeah, sadly Larry passed away in 2017. So Rich Walker, who I also work with, was there, has to pick up my referee rights.
That's a big figure.
Mm.
Shall we make a start?
Yeah.
So welcome everyone who's joining us in the room and who's joining us on Teams for the first seminar of 2023 as part of the BES research seminars. So we have Amy Riches here today with us from Edinburgh, who's going to present, and Christian is going to do the introduction for me. So over to Christian and then over to Amy.
Yes, so thank you everyone in the room for coming to the seminar, and thank you everyone online for joining. So it's my pleasure to introduce Amy Riches. Well, we got to know each other in the process of organizing the conference last year. So Amy was the conference chair and the initiator of that conference, the inaugural Forming and Exploring Habitable Worlds conference that took place in Edinburgh. And I and Emily, who's also in the audience, here helped a little bit with the organization. Amy is currently a visitor with the Earth and Planetary Sciences Institute of the School of Geosciences, the University of Edinburgh. But she trained in geology, geological sciences, and through postdoc positions in the US, she worked with Larry Taylor on lunar material. Yeah.
Everyone else was working on lunar, and I worked on other things while I was with Larry.
Okay. Yeah. And then in Canada, where you really started working on meteorites and so on? No?
No, Canada, I went back to working on earthly rocks from the mantle deep inside.
But now you're working on meteorites.
Yeah.
A lot. And that's what you will be talking about today in the first half of your talks. And then you have a second talk where you will talk about equality, diversity, and inclusion matters, because you are a founding member and were a co-chair of the European Association of Geochemistry's Diversity, Equity, and Inclusion Committee. You've also been paired with a parliamentarian, Ian Murray, MP for Edinburgh South, I think.
Yeah. Shadows that produce.
So yeah, so high position there. And you will tell us a little bit about that later too. So thank you very much.
Thank you, Christian. Yeah, thanks for having me here today. So essentially messages from meteorites. So we're talking about what we can learn from rocks from space. And as you can see here, sometimes when they fall, they hit something like a car. So that's the Peekskill meteorite, as it's called, because that's where it fell. And then we also have a lot of meteorites are quite pretty. They are collected by people. And so you can see here an image of the Fucan pallasite, which has been thinly sliced so that the light shines through the olivines, shown in sort of an orangey tone. And then the darker areas of that are largely metal. So as I said, I'm attached to the University of Edinburgh. I'm also an affiliate scientist with the SETI Institute in the USA. So what are meteorites? And we have some terminology that we deal with when they're coming into us. So a fragment of rock that's been broken off an asteroid or any other body within the solar system, as that travels through space, it's termed a meteor. As it's falling through the atmosphere of Earth, heading towards the ground, that we call that a meteor. You often see them as fireballs, as shown here. So this is Mount Rundle near Banff. I was in Canada. It's not my photo. Just want to say that. And then if they're collected, if they fall to the ground, and they're termed a meteorite at that point, and then we can hopefully locate them and collect them. So there are people who use camera networks around the world to track the shooting stars or the fireballs through the atmosphere, and to then triangulate where things are falling, as one method of collection that's come about these days. If it's collected at the time that it falls, it's termed a fall meteorite. If a meteorite is picked up at a later date, it's termed a find because it's been found. Okay, so overall, what are we dealing with? Well, there are concepts from how the Earth works. So we have a very Earth-centric way of thinking when we've trained in geology or environmental sciences, and we are looking at the connections between the the different materials on that planetary body. So a geosphere, biosphere, where we have life, as is the case for Earth, atmosphere, and obviously the water cycles and other things as part of the hydrosphere. So we can take the frameworks that we have for Earth as to how these different spheres work and connect, and take that thinking and move it across to planetary sciences. One area that we want to look at is looking at how the Earth arose, why it looks like it does today, and what happens during those very early stages of building a planet. What do we need in terms of ingredients in a planetary body to make it habitable, so life can survive there? And what happens during those processes? So there's a broad theme at the University of Edinburgh. This building worlds is the umbrella kind of concept that connects across several disciplines. And we're essentially talking about solar system science. So we are looking at rocks potentially from Mars, for example, which is among the rocky inner planets. We may also get fragments from the asteroid belt, which sits between Mars and Jupiter. And then we don't really have samples, but we have data from, for example, space missions for some of the gassy giants further out in the solar system. And we're now beginning to get more and more data for areas of the Kuiper belt. There are missions heading there at the moment. So it's really exciting, and I'm sure with Christian here in the department and Emily around as well, that you've heard about Mars sample return. So that's something that is a really exciting prospect for the future. So some examples of why it's important to understand meteorites and what happens when they come in contact with the Earth are, of course, meteor craters. So one example here is the tourist center of Meteor Crater in the US. There are obviously, the lunar surface shows you that there have been a lot of impacts over the whole history of the solar system. As you can see, many pot marks on what we might term the death mask of the moon. And modern day people like to consume meteorites, apparently. So there is meteorite infused wine and cheese available. You can even buy this in supermarkets if you so wish. But you might want to think about which meteorites are being used for that purpose. So we can study impacts, and we can think about concepts of additives, which relates to some aspects of the work that I do. So an example of a really big meteorite impact is, of course, the Chicxulub crater. So this is off the coast of the US and South America, and sits just on the edge of the Yucatan Peninsula. It's actually a buried crater, so it's been shown through geophysical studies to exist as this sort of circular depression in the ocean floor with a small peak in the middle. This crater was formed around 65 million years ago, and this coincides with the Cretaceous-Paleogene boundary, and that's really significant. So this is a period in geological history that we know a lot about, and that's important for some particular animals. The crater itself is about 180 kilometers in diameter and 60 kilometers deep. So it's a really big crater and a large volume of rock that was displaced and disrupted at the time of the impact. The impact itself was incredibly energetic, at 200 times more energy than the largest ever detonated man-made explosive device. So many, many times more than some of the nuclear explosions that we've had in the past. Which we have our own views of course. So the dinosaurs were around at that time. Unfortunately for them, it was a really massive and disruptive event with significant environmental disturbance and consequences for the existing ecologies at the time, resulting in mass extinction. Okay. So moving on from studying how meteorites interact with life, both in terms of extinguishing it and then also, of course, with the subsequent proliferation of different forms of life, the rise of humans, for example, we can also look at fundamental questions of how planets are built and constructed. So we're dealing with accretion and planetary growth. The oldest solar system objects are over 4.56 billion years old. And these are the little white materials that you can see there. So this is a slice through a particular type of meteorite. which is really useful for looking at the very earliest aspects of solar system history. And then those whitish patches within it, these tend to look a little bit cloudy. Those are termed calcium aluminium inclusions because of the high concentration of calcium and aluminium within them. And then specific minerals within that little cluster are super useful for getting really precise age dates. So this is one of the oldest fragments ever dated. And that tells us something about how you put together the rubble piles, the primitive bodies of the solar system, which then subsequently, get big enough and hot enough, have enough energy, both from the impacts and the melting that results from the short-lived decay of radionuclides. So release of heat through those processes gives you widespread melting, and so you get a formation of differentiated bodies. So by differentiated, we mean that we're segregating a metallic core and a silicate melt and a crust. Ultimately, of course, we go from those processes and jump to where we are today, where we have the Earth-Moon system. We have a watery Earth, and there is a lot of life on it. This area, formation of differentiated bodies, tends to be where I spend my time at the moment. And of course, there are all kinds of questions. So whenever we get a rock from space, we've got a lot to ask of it. So we apply our, detective tools. I don't know, those of you who like things like, what was I watching? I think I grew up being inspired by some of the people we see on TV, such as, the cold case investigators, so people who are looking at forensic sciences. So we tend to think like they do. So in terms of the rocks from space, where do we go and collect them? So as I said, sometimes, very occasionally, there are these falls where they're being triangulated and trapped through the fireballs associated with their entry into Earth's atmosphere. Those can be picked up as long as they fall in areas where they can be found. So we had the Winchcombe meteorite in the UK over the last year or so that's drawn a lot of attention. But a lot of meteorites, the vast majority, are recovered as finds and often in desert environments. So if a meteorite will often have a black fusion crust around it. So that contrast to the color of ice and snow, and also, the desert environments that you see with lots of sand in. And so that in that way they can be spotted. There are other ways of identifying them as well. There are concentrations in particular in terms of how the ice flows in the Antarctic. So we do have a UK group that relatively recently went down to recover meteorites from the Antarctic. Japan and the US and others have been doing this for a long time. And hot desert finds, we often have those from Africa, called Northwest African meteorites, so NWA, and then some signifier number. And here we've got a picture of the Atacama Desert. So this is in Chile. And a lot of meteorites are also collected and recovered from there. And then those of us who want to do the science on these samples, we have to apply for them. You write a request stating what you would like to do with the sample and why. Is what you're doing original? Has anyone else done it before? Have you tried similar things on other samples, so therefore have the expertise to receive these rocks? And then they'll come in the post. So often you're requesting samples from museum collections, or there are a few government-held repositories, often under the space agencies. And I just want to briefly mention that there are many different types of meteorites, all of which have their uses and abuses, but we can use them to probe different aspects of the history of the solar system and the formation of planetary bodies within it. Those of us that are trained as a petrologist who look down a microscope at thin sections of rock, that's often where we begin. So we start to look at the sample and characterize, describe what we see. Are there different parts of the meteorite? Because you're getting a sample where it doesn't have a known geological context. So even one single meteorite might have a number of fragments within it of different lithic class, different fragments of rock, or it might be one thing together with various different crystals that you want to look at. I just want to mention, of course, that the UK supports the Virtual Microscope project. So you can look at a number of rocks from space, lunar collections, and also some of the Scottish meteorites through the Virtual Microscope website. So that's a really great tool. We can also, at this stage, characterize the sample using other techniques. So we can use scanning electron microscopes that describe the composition of the minerals, and you get a false color image that represents where each color shade will represent a different mineral. And you can compare that to your petrographic observations, maybe where you saw different areas within the sample, and you can also blast them with laser beams. So it's a focused beam to constrain the composition of individual minerals within a meteorite. And of course, we can also process them with acids and high pressure digestions and all sorts of fun things in the lab to tease out the chemistry of the samples, which that chemistry will give us a fingerprint of the history of the sample and what it's telling us about how the solar system works. So some of what I do is isotope geochemistry, so really looking at really high precision measurements, some of which are radiogenic, in order to look at the long-term history of the sample. So you might be familiar, particularly if you're a geologist by training, of Goldschmidt's classification. So this describes, it groups the elements, not just in terms of the periodic table, but we can group them in terms of how they behave on Earth, in terms of the geology of the Earth. So some are in red here, a lithophile, they love silicate minerals. Some are siderophile and love the metal. Some are chalcophile, so they love sulfur and sulfide minerals. And some are atmophile, so they tend to be in the atmosphere on Earth, right? So this is for the Earth's conditions, which are not the case across the solar system. So we also have, for planetary science, across the chemical periodic table, and that just describes the behavior of elements in terms of a gaseous nebula, how they condense out, which ones condense first over refractory, and then obviously moving on to highly volatile elements that ultimately end up on our planetary bodies. This is a really complicated diagram, so I just want to try and briefly introduce that we can plot the chemistry of our samples and what we infer for the whole body of a planet or an asteroid or a planetary precursor in ways that allow us to compare them to other planetary bodies. So this would be comparative planetology. The grey bar on the right, which has a slope then on the left-hand side, it describes the broad trend that we see for Earth. You can see that there's an arrow there showing that Mars's slope is different to that for Earth. The APB, as it's indicated there, is something called the Angrite parent body, which is a precursor to, it's a very early formed melted body, which we think is a planetary precursor. And that again has a very different trend. So why are those trends different? And what is the importance of that? Well, those elements toward the left describing volatile element abundances in a planetary body. And so we know, of course, that water, for example, is incredibly important to life. And so understanding those elements tells us something about the habitability of a planet, the ability for that body to support life at some stage. We can also look at stable isotope composition. So one way of doing that is to use an ion microprobe. In this case, we took the measurements in France, but we also have an ion microprobe facility at Edinburgh, of course, which is the UK centre for that type of measurement. And that takes a spatially resolved measurement. So we're looking at in this case, the sulfur isotope compositions within specific sulfide minerals. And we can compare that to some data that's available. This was a Martian meteorite, so there is samples. There are reports of mission data which which we can compare to, which we did. And so this was a student study looking at deciphering extraterrestrial volcanic edifices and capturing just that whiff of surface and atmospheric compositions through the light elements. So it's telling us something about Mars by looking at a meteorite that's fallen on Earth. Another example here was some work I did during my Marie Curie fellowship. There's another type of meteorite that we can use to look at certain asteroids. In this case, NASA's Dawn mission, this is the US-led mission, went to the 4 Vesta asteroid, which is a relatively large asteroid in the asteroid belt. And because that mission went there, there is some reflectance data, spectral data for the surface of that asteroid. And knowing that there is a certain set of compositions, we can tie a certain meteorite group to that asteroid, and then we can study those and make all kinds of inferences, which is really exciting. Being able to tie our meteorites to known bodies gives us more meaning. However, there are a lot of samples that don't have known bodies that we just refer to as a parent body. We don't know which body within the solar system it is. So if we look at very ancient targets, for example, those give us the precursors to planets. So if we want to understand how Earth came to be as it is today, we have to whip back in history beyond the 4.51 billion year ago moon forming giant impact and look at just those relics from the very, very earliest first few 100 million years of solar system history. What was happening? Was it things were growing really quickly, we think, and so how did we come to put together the right recipe for Earth? Is that repeated anywhere else? Which components came together and where did they come from within a widespread molecular cloud across the solar system? Yep, so I just wanted to show you an image of the moon forming giant impact. It's very exciting. We can study that as well in great detail. So we might look at, for example, angrite meteorites. And so I just wanted to mention that the student project, this is the one that's ready to go. The samples have arrived, and so that's one set of really exciting meteorites. They are my favourites. We're not meant to have favourite rocks, but angrite meteorites are particularly fascinating. They're also, as you can see from the images, look how good the minerals are. They have really nice edges. They're relatively fresh. They give you a true picture of what was happening on the angrite body, because a lot of meteorites, when they're blasted off, they are, they've gone through an impact process that breaks them up, and so they're very brecciated. But angrites are quite special in that they're not as they don't have as high a shock history, as we call it, from being pummeled in the same way that other meteorites do. And so I just wanted to conclude the talk there, because obviously we have a 2-part session, 2 topics in this hour, and to say thank you. If you like data, there are 2 big databases, and so I just put those up there at the end. Thank you very much. Please throw your questions at me.
Yeah, so Kristen, you've got a question. If anyone on Teams has a question, then please just raise your hand on Teams or put something in the chat.
So this diagram is the different slopes for the different
Yeah.
So the Mars one is a shallower slope for the volatile terrains.
Yeah, that
mean it loses that faster or retains more. Would it have had more water than water?
Yep. So there's obviously still a lot of debate around Mars's original volatile element inventory, as we call it. Yeah, there has been a recent study that it implies that a lot of the volatile elements on Mars's surface, particularly the water, are trapped in minerals that are result from alteration on that surface, and so actually quite a significant, or potentially the entire original water budget that reached the surface on Mars is still there. It's just trapped in these minerals. That's one interpretation. But because Mars has lost its atmosphere and it's not as well protected, because its magnetosphere is weak, that we can lose volatiles to space from Mars. And so what it has now is a lot less than what it may have had in the past. But obviously, Mars is something that we really need to understand a lot more about, not just what's on the surface, which is what most of the samples tell us about, but we want to try and understand what's inside Mars to understand it, because these are bulk planet estimates or calculations. So that's always a tricky problem, because normally the main mass, the volume, is inaccessible. It's the mantle and the core, right? So understanding the inside is incredibly important to understanding the whole, and you don't understand the surface until you understand the inside in total. They're all connected, like we are as a community.
Any other questions in the room?
You said about meteorites that come through the atmosphere.
Yep.
How is that doing? How far are they?
Okay, so this falls into the realms of astrophysics. So therefore, I'm not an astrophysicist, but the tools and techniques to track these exist. It's the same as how we track satellites and space debris falling into the atmosphere. So obviously those things we need to know where they're going to fall, and so having the ability to then transfer those techniques and track meteor fireballs, and hopefully get what we call the meteorite dropping fireballs. It is something I think which is it is well developed. There are a number of people working in that area. What's important is there's an enormous amount of public engagement over that. So they've developed a lot of apps where people can report if they see a fireball. That then allows people to look at triangulating from the observations, especially if people have taken a photo of the fireball, but also then to visit that area and track down camera footage from security cameras, from dash cams in cars or on bikes, and yeah, to use that to triangulate. So that's something that is emerging extremely fast right now. There have been just over 60 over the years of recovered fireballs, but the advantage of this is, of course, that you can go in both directions. So you can also backtrack and get an understanding of where that meteorite came from within the solar system before it entered Earth's atmosphere. So that's really important for sort of building up that picture of where things are located. That answer your question? Yeah. Okay.
Can I ask a question? I'm Ebenezer. From the introduction, I'm mainly aware that the Earth was formed from space, if I'm not getting it wrong.
Yeah.
And if so, what makes the study of meteorites so unique as compared to all the rocks that we have on this Earth? Thank you.
Yeah, that's a great question. I probably have a spare slide for this somewhere among my many spare slides. Yeah, so one of the ways, so we infer a meteorite is a meteorite by looking at some of the characteristics, like looking for a fusion crust, but we don't accept that anything is a meteorite until we start looking at the geochemistry. Yeah, this one will do. So, for example, if we look at the isotopic composition, or the ratio of 16, 17, and 18 oxygen, one to the other, so 16 being the denominator in these cases, then we see that the Earth and Moon define a specific trend, and other meteorite types define different slopes. So we know that they're different isotopically, and that those constraints are really important. And then the way that we kind of take that slope and transfer it across to the diagram on the right, where we're looking at the cap delta 17 oxygen, then we've got the terrestrial fractionation line there, which is for Earth and Moon. Although some really clever recent measurements show that there's maybe a slight difference for the Earth and Moon. But anyway, most other meteorites, they have very different cap delta 17 composition. So the HED is shown at the bottom, Howardite, Eucrite and Diogenite meteorites. So this is a particular type associated with the Dawn mission's 4 Vesta asteroid target. They have a different trend to that of the Earth and Moon, and angrites are shown there, and Martian meteorites are also shown there. So these define very different isotopic groupings, and there are other chemical fingerprints among these which differ. So they tell you something about how planets have formed different stages and whether there is compositional variation across that original molecular material across the nebula as it was collapsing to form the sun and the planets and the asteroids and the moons. Okay, presentation 2 has less slides. So where are we? Is that up on the screen? Yeah. Okay, so part 2. Obviously, we can't do science without people. Our people really matter. We also can't share our science without people. But do we have everybody working in a way that's representative of populations within a given nation, but also globally? You know, or is there a dominance among certain groups? And what does that mean for how we think in science? Because we need people who think differently, right? So we can't all be the same, because otherwise we all come to the same conclusion. And in science, I think controversy is not always liked, but controversy is really important in science. If someone has a different idea, but actually the reasoning for it means that it's feasible, then it's a case of telling the community, okay, prove me right or prove me wrong. And it's important that we have those people who come up with those really kind of bright thoughts, but also new ways of making measurements or approaching a problem. So as mentioned, I served as until it's a big role. So until recently, I've now it's time to rotate. It's for Diversity, Equity and Inclusion Committee. That committee in itself, a group of people who are there to help improve diversity within science. We ourselves as a committee need to keep rotating so that lots of different people get a chance to have a say. So I was one of the founding members with the European Association of Geochemistries, which is a professional learned body for our scientific subject area. I was a founding member and also the co-chair of that committee, and that kept me really busy. And the UK contingent of that committee, we were quite a high number in among the founding group. Our UK wing kind of split off, and we managed to raise funding through a call by the National Environmental Research Council. So we also have an EDIAL, as it's called, project group, which studied the UK geochemistry community. And although that funding ended, that project has happily gained support to carry on a little bit at the Open University, where it was PI'd and based, with my colleague Pallavi. So as I've just said, science is powered by and strengthened by diversity. People need to feel included, inspired and involved. And then I think the rest of this kind of talk, I really would like it to be quite interactive. So that's just the title slide. Obviously, if we want to make a difference, then it's up to us both individually and collectively to get on the case, hopefully. So how do we go about informing and influencing and shaping change for science? So, the people that are coming into science, who we reach out to, who we inspire, how old they are when we inspire them, where they are on the globe. And also, we often, I think we've all paid a lot of attention. The cost of living has been on the news a lot. And so, funding is a major factor for education and also for research. So just to bring up some kind of prompts here, if we're going to think about how we go about influencing policy, So policy is very broad. There could be policies within an institution. There could be policies at government level. There can be policies or coordinated approaches in regions. There's an enormous amount to think about. So often we might be values based if we're starting to get involved in that. There might be priorities, strategic or otherwise, in terms of how we grow the community. Who do we need now, in 5 and 10 years' time? The structures that are in place, do they work well for everybody? What criteria do they have? Are those criteria appropriate for all people and the pathways that they may have followed? Is the timing of certain decision points appropriate for everybody? Policy is also linked to regulation, and as I've mentioned, allocation, so funding or other forms of allocation, infrastructure or ease of access, that sort of thing. Legislation, of course, deals with law. So there are policies which are written as guidance, and then there are policies which are in fact law, and so people have to adhere to them. This might link to regulation. It also might link to things like employment law or other matters. And in any case, tackling these things, they're quite big, right? So we are stronger together because it's too much work for any one person to do. Is anyone here involved in working with policy in their job or voluntarily? Yeah. And what is it that you do?
I check policy group with policymakers in Scotland that focused on bringing ecological science more into.
Yeah, great. So that sounds like science for policy. Yeah. So yeah, there are kind of, as I'll kind of mention, there are all kinds of pathways. So one is obviously through a committee, such as that under a learned society. There are ways that we can engage with specific decision makers or policy writers. So those are direct. And our indirect ways that we can campaign, we can sign petitions, we can do lots that way as well. And isn't it nice to put the word diplomacy into some of the work that you do? I was advocating for, and I was serving in a diplomatic manner, so this is how you speak to people, in other words, how you caught their interest, and how you represent perhaps your subject area, or certain things of which you're passionate about, be it your work or your community or both. And this can obviously be at national or international levels. And yeah, there are all kinds of labels on this diagram, but essentially talking to people or engaging with people, making information available, can be helpful in all kinds of ways, to, and at all kinds of scales as well, which is great. So it's not restricted perhaps to one subject area, but it might apply across all the sciences, or if you're looking at higher education, then all disciplines. Then yeah, it's kind of fun to do. I never really thought that I would end up doing something like this. I come from a very, very different background, so yeah, everything is exciting and new every turn. So I've kind of mentioned things like interpersonal skills, the way we get on with one another, and sort of, yeah, kind of getting involved with this work gives you skills in all these different areas, and obviously influence, hopefully, as well. People often make you feel good if you've spoken to them about something and they go away and you feel, oh, it's all going to change overnight. Doesn't always happen, but keep at it. So a lot of what I've been doing recently is policy for science. So looking at helping the community, not necessarily taking hard scientific results and putting those into policy, but rather looking at the structures that we work in within sciences, particularly our European relationship as well, and making sure that hopefully that whatever we find about our scientific communities from studying them, that we make that information available to say these are the areas that need to improve and perhaps make suggestions. And then, of course, we've heard that you can also take the results that you have from science and use that to directly inform policy making. Okay, so I just had some examples listed up here of what we can do. Of course, people who work for government are openly contactable. So should you have a concern or an area of interest you want to engage with, you can always email somebody. They may reply. That's always a good start if they reply, because they will sometimes receive many hundreds of emails in any given day. But you can speak to civil servants, government officers, relevant ministers, and also cabinet members. You can feel free to contact them as well, which is great. There are, of course, formal pathways to do this. There are schemes that you can sign up for within Scotland, the UK, and more widely. If anyone wants a list, I have one ready prepared, like a Blue Peter presenter. There are sometimes calls on an annual basis, for example, to say, what would you like us to look into? We want to do a government inquiry. What areas should we be looking at? And you can submit suggestions. Those are open call, so you provide a short summary given the reasons why, so you can turn government attention to your area. Can contribute. You might be called to go and speak as an expert, which is always exciting, an enormous responsibility. In the same way that there are committees that we perhaps join within our institutions or with learned societies, there are also committees and other groupings within a given parliament. So there's often just information across websites. You might have to search to find it, or you might want to find, the right person who can point you in a certain direction to take your science forward or your interest in your community. And there are often evidence calls, which might be open appeals. So they often have a theme. So there have been evidence calls from the UK government for example, diversity and inclusion in science. And so if you have some evidence that's relevant to that area, you're encouraged to submit it. And then the government can obviously process that, take action as needed. And of course, government itself really likes scientists. In fact, it has many scientists within government. There are people who are still working within the scientific area, but there are also, of course, MPs who were once scientists or trained as scientists originally. There have been prime ministers who gained degrees originally in science subjects. So this is really important. It's really important to have scientists in Parliament. You want members of Parliament to have understanding of the concepts, at a reasonable level. So it is good if you're thinking about this type of thing, or if at least you're aware of it and it might be something you think about later in life. You can go forward and make a difference directly that way. There are also people who are, the House of Lords is always a controversial matter, but it does provide specific expertise. So there are people within the House of Lords who are recruited to that for the expert knowledge that they can offer. Oh yes. So one thing that I did that I was going to tell you about today. Has anyone else been to Parliament? No, Westminster or Holyrood? Holyrood, yeah, right, yeah. So it was still indoor. So it's great to go. I wasn't aware that there was a pairing scheme until it popped up through social media on the deadline day. So I applied in the manner that you're not meant to at the last moment and emailed my referees afterward. But it's a competitive scheme. You can apply to be paired. Often the pairing is with your local MP, your local member of parliament. So it's obviously to do with constituency matters and then facilitated forward from there. But there are people who will also choose to be paired or request to be paired with someone, you know, that might be serving in the Science Technology Committee or otherwise, and has you know, is specifically working on something that they want to discuss with them. I had a really good time. I was really fortunate to get this role. So I think there was over 300 applicants, and then there are something like 60 of us that go down in a big group. And then 30 of that 60 are paired directly. So I was paired with Ian Murray, who's the MP for Edinburgh South. He's also Shadow Secretary of State for Scotland. But what was good about that pairing, you're not with them the entire week, and the experiences that people had varied. But for my pairing, I got 4 hours, 4 whole hours to discuss whatever I wanted with Ian. Now, I wasn't warned about that ahead of time, so I hadn't prepared specifically, but that was great. So, you know, what can you talk about for 4 hours with somebody who's going to make decisions on all sorts of things? Well, you can talk about the Equality Act and how that relates to employment in general, but is maybe specifically relevant to science. And, you know, then we can also talk about science, which is nice as well, and what's going on in that world. So, you know, this is Edinburgh, Scotland, so we could talk about the context for space and planetary sciences. Here we could talk about the city and region deal that exists for space and satellites, but how narrowly do you define that, and where could you broaden it out? And as it turns out, we ended up talking about the Fermi paradox, which is, you know, deals with the likelihood of life in the cosmos. Not my direct subject area, but fortunately I've read widely enough to, you know, be able to at least say a sentence or two on the subject. And it's not just Ian that you're speaking to, you're often speaking to team members. So because he's a cabinet member, he has, you know, shadow cabinet member, he has a team of people, which is great. So you they can run off and take information to the relevant people. They can get the wheels turning in various areas. So I don't know if anyone, you know, ever fancies doing this sort of thing, but there are schemes. There is also a recent Science in Parliament event at Holyrood, so you can, you know, pop along and attend specific things. This is financially supported, so your travel and accommodation and everything is all provided for. And then when you go to the Science in Parliament thing for Holyrood, the day itself is free. You've just got to get there, and that's just a day, whereas the Royal Society scheme at Westminster is a week. But the Royal Society were present, and it would be interesting to see whether they're trying to facilitate a similar scheme up here for, you know, more extended pairings. But this is great to sign up to. So if anyone is ever wanting to do something like this, or even to just dip your toe in, I would recommend it. So as I've mentioned, there was this other event which involved all sorts of people. It was fun to do. Did anyone go other than me? No. I told Christian at the last moment, didn't I? So they sold out of places at that point. And Emily, I think I was intending to tell you too. So, and Jarita, who was also on our team for the meeting well, she appeared and joined in as a colleague at Edinburgh, was very keen to be there, extremely keen, but again, they'd sold out at the time. So yeah, she came and joined in at the edges. But it was great forum, not only to kind of hear the views of members of parliament, but also there were many sort of policy groups there represented from learned societies and others, so you could interact with lots of people who are, this is their job, you know, some of those people are employed in positions to do that work. So that was great. Teamwork makes the dream work, as always. So we're coming up to the end of our time. I did sort of frame some questions. So higher education and other, we live in a world where we have to rank everything. You go in a shop and you're asked to leave a score. You know, your delivery person comes and you receive an email immediately asking for your mark out of 5 for them. So we live in a world where there's a lot of rankings. Now, whether that's a pro or a, you know, a questionable way of considering excellence is always up for debate. So here's the question: are the you know, the levels of diversity and how comfortable people are, so how well they're included and feel they belong, how important is that, and is that the real measure of how successful we are being, both in our research and in education? So we might think about people's attainment. So we often monitor attainment through educational pathways. So we're looking at how well people's promise and performance match up, and whether there are any, you know, systematic differences among different groups of people. And that also relates, of course, to careers. So are people getting the same opportunities, or is their identity in any way a factor? You know, at all stages of your career, whether that's within higher education or wider areas of science and other employment. Are things publicly accessible to all people of the public? So people with various different disabilities, for example, and is our work released to the public in ways that is inspiring? Are we also connecting efficiently with small, medium enterprises, so with business areas, and downstreaming the types of findings that we have or inventions that we come up with? And when we are connecting with business, is that also done in a way that is equitable for different people? And then obviously we want to consider things like the influences that committees, panels and leadership have on subject areas and on education. You know, so who makes up those committees, panels and leaderships, both now and, you know, over the past couple of decades, and who will make up those members in future? And are the contributions that they make through those areas equally recognised? Because if you have, for example, a room full of people and you only have 2 or 3 people who are female, for example, but they're always asked to be representatives of all women, you know, by sitting on an enormous number of committees, for example, that's an enormous burden on them. But is it recognised as a valid career contribution, for example? And we're also considering intersectionality, so that really relates to whether somebody is has an identity which is across a couple of different factors. So might be to do with race, disability, gender, identity, or otherwise. So there are published reports. There are enormous numbers of reports, and a recent one here really looks at the results of funding applications among people with different identities. So you can see that overall, white people dominate, and in particular, we have a large dominance of white males across all areas of UKRI. So the UKRI is the research and innovation body of the UK. So does anyone want to make any comments on this figure? Is it an expected result? Are you nodding, Emily? Yeah. Okay. And obviously there are areas such as Black women are often in a stark minority relative to their numbers in the overall population. We can think about how we might influence how investment is targeted, and is it being targeted in ways which are really efficient? So providing feedback or just influencing how that is being invested in the first place. So thinking about education and skills, thinking about careers, and the structures that people face in those careers, whether there are fast track routes for people, particularly for minorities, they're given appropriate support. As I've mentioned, the way that public access works, the way that we downstream things, yeah, and how we coordinate all of our efforts. sometimes government can come in with an umbrella scheme, city and region deals being one example. Any comments? So the images just show, you know, someone who has relative privilege over others, and yeah, hopefully we'll get to a point. I didn't want to show you results for the community. There's so many studies, but essentially, you know, we are largely white male dominated in the physical sciences, and we also have a problem with a lack of racial diversity. So yeah, those are things to tackle, because we know that they're widespread. They're not just sort of, you know, results here and there. They're consistent across big groups of people and across a number of subject areas. So that's one area to tackle. I was just going to say that I find it really rewarding. It's like teaching. The more people that you engage with and the more people that you can see feeling comfortable with what they're doing, you know, you feel happy about your own work. And you know, and you enrich that environment because there are people there who think differently, so they're going to throw up really good ideas. So yeah, it is something which takes a lot of people and a lot of energy. So over time, you know, join in when you're able, and but join in, and do so, you know, over many years. Keep at it. So I guess that's everything. Thank you.
Thanks, Denise. We've got a couple of minutes now. If anyone has any questions or comments. Yeah.
It's a little bit of a personal question, but what were your academic options or the pathway that you followed that resulted in the position you're in now?
Okay, yeah, that's a great question. So how far back should we go? So at school, I did well in school, which was quite unusual for someone in my family. So I come from a background where nobody has gone to university before I did. None of my uncles or aunts, none of my parents, and no grandparents. And so, you know, a lot of people have really important jobs in building and construction and, you know, automotive, so being a mechanic and working in the agricultural industry and that sort of thing. So yeah, I did well at school and I had some great teachers. They also, it was in the, because I lived in the countryside, they're small communities, so people get to know. So like the local doctor took an interest and the local solicitor took an interest as people who hold degrees among that population. So that was good. So I was encouraged to go to university, which I did. I went to Durham, which was relatively small, so I didn't find it too intimidating as a place at that stage in my life. And I wasn't sure whether to do English or geology. Obviously, those two subjects are very similar to one another. But I ended up doing geosciences. Once I started, I really enjoyed it, so I continued on with that. I didn't have parental pressure to do any particular subject. They said, if you don't like it, you can always change to a different one. I'm sure you can. You must be able to. That was their opinion. And I got a first class degree at the end of that course. And it was difficult financially, obviously coming from the background I did, to get through, pay for field work, do all those kinds of things. But I got through at the end. I was lucky in that I had a really good final year project that I really enjoyed and ultimately was published. And that set me up to apply for master's and PhD programs, which I did, and I had a few offers, but I took up a PhD at the Open University, looking at the mantle of the Earth, so looking at melt rocks. So I trained as an igneous petrologist and a geochemist, so looking at the chemistry of those rocks, and And that was really good fun. But I was in the Earth Science department. There is a big planetary institute at the Open University. So there were people around who did that kind of work. And it was sort of by accident when I was applying for my first postdoctoral position, so my first research job after gaining my doctorate, that I ended up taking one in the US. I didn't know that studying pieces of Mars was a job, but it was. So that was the first project on that postdoc. It was a really busy postdoc. I didn't really recognize at the time the person I worked with, Larry Taylor. He's a big figure in lunar science. He's been around since the Apollo era. Sadly, he passed away a few years ago. But yeah, he was involved with looking at rocks from the moon, which I didn't work on while I was with him. I had my own interests, so I was fortunate in being supported and working on some meteorites that I liked. And that was good. And then I took up a postdoctoral position at Alberta in Canada. Again, that brought me back to the Earth, but it was a big, the person I worked with was a Canadian Excellence in Research chair. Those were new appointments that came with the ability to create big lab space. So I was involved with lab building while I was there. And then I applied for some funding with the European Commission as a Marie Curie Fellow, which I succeeded in gaining. And so I was able to return to the UK on a fellowship of my own, so I could conduct my own research, which was planetary. And that was at Durham. And yeah, now I'm attached to Edinburgh. So yeah, it's good. And along the way, you get to share the science that you do through outreach, public engagement, and also teaching, of course. So yeah, it's all very rewarding. Yeah, I just want to see my experience at the Open University in particular. It's a university that works in a different way, so that really shaped my perspective on who does things and at what career stage. And because people there have come into subject areas at all different points in their life, and under a range of circumstances. So I think that kind of embedded in me this philosophy that what we do should be for everybody, especially if it's publicly funded. It's in service of that public, so everyone should be there and have a voice and be doing that work. Yeah, so that's just a hobby, really, in addition to my science. But yeah, important to be involved in.
I think we have to end this timeline.
Yeah.
I don't know, Amy, if you're sticking around for a little bit of time, and then when has any questions afterwards, I'd like to discuss with Amy. But yeah, thanks again to Amy, and obviously for the board chairman. So, thank you.
Thanks.
Thank you very much. Warren, I'm about to turn the lights back on.
Yeah. Sorry, I got a bit slow at the end there.
No, it's okay.
Waffled on a bit.